And now we discuss about the model deployment. So again, recapping, we were within our build pipeline. The final step of the build pipeline was to register the model and basically publish the build, the machine learning pipeline that we generated, right? That was the basic end goal of our build pipeline. But before we get to the deployment, let's discuss about some of the concepts about what are required to get a bit deeper understanding of what's going on there. So first, discuss about the containers and the journey to containers. So in late 90s and early 2000, whenever anyone wanted to basically host an application, they had to have a physical hardware, literally as a server, and have everything installed on there. So imagine that becomes a big mess, right? Having like 10 applications installed on the same server, so many dependencies, we'll have a lot of conflicts with each other. That would create a big mess and big confusion. Also at the same time, you cannot run some of the, like you could not run Linux and Windows at the same time on the same machine without virtualization, right? So you could not leverage probably the entire hardware you had. Some of them were underutilized and not very easy, basically was able to maintain that. Also, makes your code impossible to ship. It's really hard to keep track of what you install, what packages you've installed, what libraries or dependency you have installed, and what dependency for what application within that server. It becomes a big mess of and hell within that environment. Then there was a virtualization got introduced. So within the virtualization, the whole concept is that you have a host operating system like you have Linux, and then in the hypervisor or virtualizer like VMware, for instance, you would be able to run multiple operating systems at the same time on that physical hardware. So you could specify different types of RAMs or basically different capacity or power you want to assign to a particular VM, and that will give you to consume more and basically utilize better from your hardware that is actually provided to you. But there was a big problem here. One is that you see that like this guest OS is like repeated 3 times. If you have like 10 Linux VMs, you had to copy 10 Linux operating system at the same time. It's like a huge duplication of the memory and also of the hardware. And also there is zero shareability between the VMs. So again, that was better. It makes your code much cleaner. Basically a run VM per application. It makes it nicer, but again, it's hard to ship because it's really hard to find what was the dependency and etc. for that application, and also still a lot of duplication and inefficiency. Then also there is not only the hardware problem, there was also a huge shift on the software paradigms. So previously, most of the application, if you passed like software engineering course in university, you're familiar with this like silly like UI, business logic and data layer. So what used to be an application, it was like one gigantic like piece of code, which had UI, business logic and database basically in the same code base, and the same machine had to run UI, business logic and database mostly. So it was completely monolithic design. But then there was a shift to microservices where you have very tiny little application needs a little tiny hardware to run. Instead of dedicating a gigantic machine and a gigantic application to a machine, you want to assign a little application to a little resource. So you want to basically distribute that and make it basically run a lot of smaller systems or microservices called, and then be back. And the power of this is that like if you want to change a particular pieces of this application, much easier to maintain. It's harder to write this application, but it's much faster and easier to maintain and scale. Well, let's say if you want to scale one of these and increase this like hardware of one of the services, much easier for me to do that than in one monolithic gigantic application. So because of these 2 requirements, there are some more, but these 2 main requirements, there was a containers that got introduced. It's not a new thing, it's been around for many years, but got a lot of momentum and traction. But the concept is that instead of having one VM, which actually has like a lot of duplications, you have the host operating system, the Docker engine, and basically each of these are your application, which are duplicated or copied from a particular image. We will discuss that a little later. But then the good point is, instead of you duplicating all of these operating systems again and again, all of these will run based on the host operating system based kernel. So when you wanted to basically Dockerize or run a Docker image or containers, you will package it like through a Linux, build a Linux container, and then you will be able to run it on Linux. So the good point of that is you don't have to ship or save the Linux operating system again. It will use the Linux operating system of the guest, of the host OS, instead of having it for itself. And also the other power here is that it's able to share the libraries. So you can basically share the operating system file and also the libraries between each of these applications. And makes it much easier for you to scale it up or scale it down and even make it shippable. Because each of these applications, these black boxes can be easily moved somewhere else, and they can easily run it under on any kind of Docker engines. And we generally have two Dockers, one for Linux, one for Windows, because you don't want to move the operating system kernel again. And the good point about like Linux Dockers is that you can still run it on Windows, but on Windows there's a light Linux basically running on top of Windows, so you can basically run any kind of Dockers anywhere, but not vice versa. You cannot run Windows Docker just directly on Linux machines because of that reduction of duplication, the reduction of basically operating system files, if that makes sense. So that gives you a lot of capability, like all of the previous problems of like duplication, and also the dependency are resolved. And also another good point of this is that if you follow the practices and the standards of Dockers, basically you know exactly what you have installed and what dependency you have provided for each of these little icons. So once it is shipped, someone else can easily follow that and can easily basically deploy it somewhere. So we have two terms which are used sometimes interchangeably, image and container. So the image is basically the file which tells you exactly what type of dependencies are required and what type of basically runtime is required to run. And whenever you run this, you will create a container. So similar to the concept of class and object, right? So you will instantiate from a class to create an object. Similar here. You will instantiate from the image to create a container. So you run container from an image on a Docker engine, basically. And so whenever you create an image, you can basically, when you create an image, Docker image, you can host it somewhere. And wherever you host the Docker is called the Docker registry. There's something called docker.com, which if you go there, there's a hop.docker.com, which is the public and the largest Docker repository in the world, but you can also have your private Docker repositories. If you have created something you don't want to share with the rest of the world, you can like use any cloud provider to basically host your images there. So like the Docker Hub, basically what it does, you create your image and then you push it to the Docker repository and everyone will fetch it later on if they want to use it. So the same exact concept happens when you basically run your estimator or run your submit your job within the Azure ML. So let me tell you what happens. So when you basically define your estimator or Python script, it first checks what type of compute target is required. Is it local or is it remote? So in this example, I'm actually using a compute target, which is referring to something, this object, like a GPU target, for instance. And then it checks what type of estimator I use. Do I use like a base Python script, or I want to actually use an estimator? So when it finds that it actually is using an estimator, in this case TensorFlow, and also the use GPU is true, and also if it picks the version number for the TensorFlow, it goes with an internal image repository, which all of these different configurations are pre-packaged. it ships that image and loads it into that target compute. And then it checks what type of packages are provided through pip package and conda packages. And it will, after the Docker image is shipped to that node, those pip and conda packages are pre-installed. So if you have package your image with all of those dependencies installed, you don't have to use pip install and conda install at all. So it becomes much faster. It will basically copy and deploy instead of copying that and basically downloading so many packages, and maybe you face some problems there. Then it checks whether there is a local data set or local data resource or online data resource is required, or something referenced within the cloud. So in this case, it's referring to the default data store. If you remember, there was a default storage account created at the time of creating the workspace. And because that is mounted, it basically will point out and mount it to the compute as if it is attached physically to the compute. If it was set download, it will download everything which is within that storage to that local directory. And you specify where you want to download. Of course, it's not recommended. Like if you're working on image problem, you probably have hundreds of gigabytes of data, and you definitely don't want to download. That takes half a day. Not half a day, but that takes a lot. Especially if you are using clusters, it downloads to all of the nodes within the cluster, which is definitely inefficient. But then the next step is basically to find this script folder, and everything under this script folder will be copied into the target compute. And after that, it will find this file within this script folder. Like if you remember, within that script folder, there was a tf-mnist.py and also util.py. Both of them will be moved there, and the entry file will be executed. So if you have like hundreds of applications, you can basically move everything has to be moved to the target compute. Or if you will that application, you can basically ship that and then it will be executed. And finally, once it is submitted, it will start to collect all of the metrics and everything there, right? So it would start to collect all of those 4 components. The metrics, the execution logs, the output files, and also the snapshot will be saved within the experiments. And that happens over and over every time you submit a job. So that makes your code much more shippable, because like that container can be downloaded. You can basically pull it to your local computer and basically do anything you want. The good point is that if you have Docker installing a local computer, you can, instead of this target compute, we can provide the string of local. So what it does, you basically deploy that image on your local computer and runs it on the local computer. So that's the flexibility you can get. And basically, once you have that Docker, you can run it anywhere. Anywhere which runs Docker can run this code. Going back to the pipeline, every step does the exact thing, right? Every step, it checks all of these dependencies and basically does the whole thing all over and over again. And everything will be stored as part of the experiment. All right, so now we want to integrate the pipeline that we built, right? We have built this pipeline. Now the next step, after we understood how it works, going back to that requirement, we want to integrate the pipeline within the build, Azure DevOps build pipeline. In the first session, we built a very simple pipeline, but that's definitely not the purpose. We want to integrate a machine learning pipeline inside the build pipeline. But let's see what it does. So going back to that initial diagram that we discussed, let me find that for you to refresh the memories. So going back to this file, this diagram, there was a build pipeline happening here, right? Once your code gets pushed into the source repo, based on the continuous integration or pull request, like merge or pull request, you want to kick off a code. You want to start executing a code. And that code is actually your code which generates the machine learning pipeline and executes the machine learning pipeline for you. So what happens when this step gets executed within Azure DevOps? So first, an Ubuntu machine gets kicked off because it said we want to run it on Ubuntu machine. You can set Mac OS or Windows. But it was Ubuntu 16, I want to run it there. Then what it does, it will basically set a particular Python, and then we install all of the dependencies from that repository. So first, it checks out everything to its to this VM, all of the code, finds the requirements.txt, it runs it, pip installs that, and then runs the PyTest. Then it runs the trend pipeline. What it does, it basically creates the pipeline and then executes the pipeline. So within this, what is important is that when you're running that through the notebook, through the VM, it requires to be authenticated. So you're not there to provide your username and password. It needs to be authenticated automatically. So it needs some authentication, and the authentication is the key here that we need to basically find a workaround that. So there are two ways to authenticate when you want to deal with the workspace. One is the interactive way, which you do it online, and the other is using something called service principal authentication or service principal identity. What it is basically username or entity or identity within Azure, which is built to be provided to application. So then that application can communicate to Azure. And basically based on any provisions or any kind of access control you provide to that user, it will be able to manipulate some resources on Azure. So if it is limited, it's limited access. If it is complete full control, it's full control access. You have to be careful of that. And pardon me?
Take a question.
Sure, yeah.
Is the Docker container deleted or stopped after the experiment?
Okay, that's a good point. So it will basically, yeah. So the question is the Docker, so once the Docker is shipped and all of the pip install happens there, what happens then? So it will be saved in a container repository, which is again attached to the workspace. So if you remember again, the first thing which was attached was a storage account, right? We discussed it was a storage account created at the time of workspace. There's something also else is created when you create the workspace, which is called container registry. It's a service on Azure which you can keep any kind of container images, right? So once the Docker image is pushed to the VM and all of those pip install and condos is saved, if that example is not available within the container registry, it will basically Dockerize that and ship it there and will be cached. So the next time you don't have to basically go through the whole pip installation, it will pick that because of that combination and basically gets deployed to your local computer, to your compute target. Yes, please.
But then there's like a wind down time for the instance or the compute target that you have?
Yeah, so once the job is completed, it still keeps that until the next job has a completely different configuration. It has a different configuration because every time you can only ship one image into, we can basically run one container in that machine. That will be wiped out and a new one will be pushed there. Yeah. So as long as you don't change the configuration, the same image will be used for all of the experiments. All right, so going back to this, so two steps. Two different types, username and password and the service principal authentication. So I have the in-depth steps of how to basically create this within the lab. We will go through that. But it's very important to basically know exactly how it works. So I forgot this slide. Readiness. Yeah, so what it does basically, once that service principal is created, you have to extract some information, which then will be used within that application. Like there's a different mechanism to do the login. And once that login is basically happens, it will authenticate and authorize that application. And based on that, it will be able to manipulate some resources on Azure. And in our case, it will be manipulating the ML workspace. It creates a pipeline, registers the pipeline, creates the compute targets, and then runs that, and then publishes the pipeline, right? This is basically the task that we want our machine to be able to do and accomplish. All right, now again, going back to the pipeline. Again, going through this, once the new code is committed to the Git repo, the DevOps CI pipeline happens. We can of course set it for pull request. We discussed this, and once that code train underscore pipeline underscore create.py is executed, what it does, it basically creates that pipeline. It executes the pipeline for me, and then once the pipeline is executed, it basically at the end, what it does, it will register the model, right? So if the model is better than the others, in the code I remove this part because every time I want to register a new model, but there's like a commented part, you can remove that and make it basically be sensitive with performance. But what it does is basically, theoretically, what you want to do every time you want to check whether this model is better than the previous model. If it is better, I want this to be registered in the model registry. So that triggers a new basically pipeline. So if it registered a new pipeline, means that this pipeline is worthiness, basically, is worthwhile to publish this pipeline. If this model is not performing better, it's better to ignore it, right? Because what's the reason of pushing a new model and making a new pipeline available if it's not going to do any good, right? So that will be published, and then the publish means that there is an API endpoint will be provided. And once it is provided, what it does, the result of this pipeline is one, the model which I generated, right? And also there's another step that I want to do is basically I want to copy my code which is related to the release pipeline and register it as another asset. I will show you basically how it looks like in something called artifacts within DevOps. So these two artifacts will be provided for the next step. And then the next step, which is the release pipeline, will be kicked off. So, so the important point here is that I don't want my release pipeline gets kicked off because a new training code is pushed into the GitHub. I want that to be kicked off if a new model is registered. And that's an important differentiator. That's important difference here. And that's one of the differences between a typical CI/CD and a ML/CI/CD. Where in ML/CI/CD you want to be sensitive of a new model, versus in a typical CI/CD you want to be sensitive of a new code, which is pushed there.
So,
Yeah.
So in that previous picture, when you say a pipeline is generated, it's both generated and executed, right? So it's like you update the pipeline definition if any new steps are added, and you also publish that.
Exactly, because the reason is the code I'm actually writing and the code which is changed, which is all of this is happening after, is the code which is related to my training job, right? So if I'm changing something there, I want this to be sensitive, basically.
Okay.
Yeah. And even if I'm changing something for the release, I still want to run my training pipeline. If I'm changing anything for the deployment, I want still to run my training pipeline to make sure of integration, right? Whether my training is leading to the changes I made to my release pipeline or not.
So the new model is registered, but then you don't choose to deploy it. So then in the release in the release pipeline.
So what was the question?
No. So just to clarify, so you run the training pipeline, and then that results in a model or a new version of model being registered.
Exactly.
Right?
So
but
that
you
will
don't
be saved again.
necessarily promote that model to like production.
Exactly.
That's the release.
Exactly. That's the responsibility of the release pipeline. Exactly. Yeah. It will be only saved in the model registry, but it's still not in the deployment area. Yeah. Basically, it's like a pickle file somewhere. Yeah. And again, like this is like a nice environment. You can basically save it somewhere in the model registry. But if it is not available, for instance, in like AWS or GCP, you can save it in a like storage account. So like this a little bit more coding is required, but you can basically develop the whole concept. But custom model registry should be built
But
there.
in this diagram, like with the build artifacts, like the release code. So I'm guessing that's very similar to like I guess in SageMaker where you have like scripts or the inference scripts or whatever that you save along with the model. Okay.
Exactly.
So in that particular case, you have that Git symbol, like in Azure, does it actually put into Git or like a Git repo and then has a separate repo for the model registry?
So for model registry, it is not within the Git. So it
Okay.
is outside the
Sure.
Git. But the good point of the Azure DevOps is that basically you can connect it to your workspace. You can connect the Azure DevOps to your workspace through an extension. So the DevOps can listen and subscribe to your model registry within your ML machine learning workspace. So everything you add there will be immediately get kicked off. So that's the like easiness, but of course you can basically glue that. Like you can basically generate a trigger, like add like a lambda function or function, basically get triggered whenever you change something there. So that's for the model piece only, and the model doesn't have the reference file, the inference file. The inference file happens a step later. We're going to discuss, and the code is basically within the Azure DevOps now, right? So you basically have that code and the result of the build pipeline as an artifact, because after any build pipeline, you can build some artifacts, like a result of the build.
Yeah.
So that artifact can be a set of code, can be a VL object, can be the actual model saved within Azure DevOps. We don't want to do that here because we have a better place to keep it. But one of the main artifacts here is the actual code. And because this is registered somewhere else and I can connect DevOps to there, so I'm also providing that as another artifact. Although it doesn't sit in Azure DevOps, it sits somewhere else, but I can basically subscribe to that, if that makes sense. Yeah. All right, so again, going back to the pipeline scenarios, what a pipeline scenario would do, there are like three main different types of ways you can basically run your pipeline. The first type is very simple. You write your pipeline, you generate your theoretical, like the concept or the logic of the pipeline, you execute the pipeline, that will generate a model, and that once it is generated, it becomes valuable to be getting published. The second way is basically you can divide it into two types. One, you run the pipeline in a dev or QA environment, like tested on a small tests, data, or like doing some level of testing there on the model. And once it was successful, you run it on the production environment or production data, then the same thing happens. We publish the model and then they register it. But the last step is basically you generate the concept of the pipeline, you don't execute that, you just register it. And then the next steps basically happens is, and you let the release pipeline to execute that conceptual publish pipeline, right? So you can, going back to the definition of pipelines, you don't have to necessarily always run it and publish it. You can just publish a pipeline without running that pipeline. So you can just publish it there as a result of the build and let the release pipeline to basically run that pipeline for you. So for this example, the second is used. So what we do here, we basically, the first is used. So we basically train the machine learning, build the logic, train the model, and then based on that, we will publish it. But you can of course like do the other two too. Yes, please.
The last one?
Yeah.
So is that just you declaring the
The
pipeline?
steps, exactly.
Okay.
You basically create the DAG,
Okay.
and you let the release to basically execute it. Yeah. So now going to next step, which becomes more clear. So the first step in the build, the artifacts are the code and the model, but the third is only the code because we haven't executed it. And only in the release pipeline, we save the model, and then we push it and basically we promote it to the production environment. And the production can be one production environment, and can be like QA and prod environments, basically. Very narrow example is Q&A and prod. Yes, please.
Do you have some other artifacts from the build pipeline? Like, let's say you're using some transformer in sklearn, and you want to save that, and you've defined it on the train set, now you need to apply it at test time or during inference on new data.
Yeah.
So could you save that somewhere like on blob storage and then call that during the release?
Absolutely, yeah.
Okay.
So if you have any dependency, you have to keep it somewhere. It's better. The Azure DevOps is not really a good place to keep it kept, especially if it is a feature set. It will be a little bit gigantic. For that, it's good to keep textual data max there. But of course, you can save it in a blob store or somewhere else. Yeah.